in the last class, we started analyzing turbulent flow. We looked at the turbulent velocity profile near a wall, right? And we had talked about three different layers of flow field. So we are looking at so that's the wall we have, and then for convenience, or rather we found that the structure of the turbulent flow near the wall can be divided into three parts. The first layer is what we called as the wall layer, and in the wall layer the viscous stresses are much larger. Finished. The layer which is very close to the wall, okay, where we called as the wall layer, where the viscous stresses are much larger than the turbulent stresses. And we had from dimensional analysis, we said u plus is a function of y plus, where we had defined u plus and y plus as the two non-dimensional relevant variables, as a velocity variable and a distance variable. And then we had the overlap layer, where we had a logarithmic law that we wrote down, which was u by u star is equal to 1 over k ln y u star by nu plus b. And then we had an outer turbulent layer, where we wrote down a defect law. So that's what essentially we did in the last class. Okay, so what I'm going to do now, so I'm just going to draw a diagram showing the velocity profile that's there in these three layers, and I'm going to do that using u plus and y plus. So u plus and y plus are the velocity and the distance variables that I'm going to use now throughout, and I'll keep my x-axis as log and y-axis as a linear scale. Okay, so the first part that I'm going to draw is the velocity profile in the wall layer, and that's where I have u plus is equal to a function of y plus. We really do not know at the moment what is f, but it's been now seen experimentally that u plus is approximately equal to y plus is a good enough approximation. Okay, in other words, in the wall layer, the velocity profile is simply u plus is equal to y plus. Okay, so if you use that, so you're basically going to get something like that. It's a log linear plot, so it won't be straight line. Okay, so that's what the wall layer will look like. Then we have the overlap layer. In the overlap layer, the law is already logarithmic, so in this plot it's going to look like a straight line. So I will have so it will be a smooth connection. Okay, I will have a logarithmic layer, and then you will have the outer layer, which we don't know, something else. So that's my wall layer. This is my overlap layer, and that's my outer turbulent layer. Okay, and here we already know the law. So this, the law that is governed by is that. Here in the outer layer, that's what we have plotted. Okay, now the point is that this outside layer, okay, the outside layer depends upon what is really your, so this could be multiples, meaning that one could be a pipe flow, one could be a flow on a plate, and so on. So whatever be the main flow that you have, that is seem to be affecting only the outer layer. Okay, the overlap layer and the wall layer are independent of the flow configuration that you really working on. Okay, so the wall layer, which is dominated by your viscous stresses, and the overlap layer is really independent. The profiles are independent of what is the outer flow field. Okay, the outer flow field is the only one that is really dependent upon the exact configuration that you are looking at. So that's why I have plotted a wall layer. I have plotted just one line for the wall layer and for the overlap layer, because they are like universal profiles, and then things basically start changing. All right. And this wall layer in this coordinate y plus is approximately up to 5, and the overlap layer is found to be approximately up to 30. Okay, so these are all experimental measurements. Okay, there's no way to really calculate that. If you write it down in terms of y plus up to y plus of 5, you will see that u plus is equal to y plus is a good approximation, and from y plus being 5 to 30, you would see that u plus goes as approximately logarithm of y plus, and beyond that, neither of these two laws are okay. You will start seeing different profiles. Yeah. U plus is equal to y plus is between y plus being 0 to 5. So in that region, approximately u plus is y plus. So see, only thing that we derived was u plus is a function of y plus. We did not know. Now I am saying that experiments show that u plus is equal to y plus. We did not show u plus is equal to y plus. We calculated u plus as a function of y plus. Any other questions? Yeah. I don't think it is really necessary. It could be any way, but I think these profiles are probably stable. So typically, I think you would see it like this. You can see that it's already. So for example, it was laminar, it would have been parabolic, right? So it's some signatures of like that. The curvature should be like that. The other curvature, I think the flow is never stable. That's why you don't see it. So that is actually the important point. Okay, even though we introduced overlap layer as something which is to connect these two regimes, it turns out that overlap layer is very big and it is a straight line. It's a straight line in the log linear scale. Okay, so the logarithmic law is a very robust law, it turns out, and it spans quite a length, as you see. Okay, it's not a small region. In fact, what we are going to do now onwards is going to skip the wall layer and the outer layer and going to stick or use the result of just logarithmic layer. Okay. Okay. So now we are ready to look at turbulent flow in a pipe. What is our ultimate aim? Our aim is to get the pressure drop, which we would write it as using friction factor. Okay, and we want to relate friction factor with Reynolds number. Okay, that's the aim. So F was is equal to 64 by RE was the relation that we found for the laminar flow. We want to now get a similar relation for turbulent flow. So that given Reynolds number, we can calculate the pressure drop. So what we are going to assume now is that, so the first approach that we had, right, starting from the governing equation is going to be impractical. So what we are going to do is, having seen that this is the particular structure of the turbulent flow, and wall layer being very small, we are going to assume that overlap layer is majorly the the velocity profile inside the pipe. So in the pipe, if you have, the wall layer will be very near to the wall, right? And then we have a large region of the overlap layer. So let's say that we will just use the overlap layer as the velocity profile and try to see what is it going to look like and how does it match with experiments. And what we are going to see is that it's going to be a robust approximation, or the approximation that the entire turbulent velocity profile is given by that logarithmic law is a good approximation. But we have to do it and see that it's a good approximation. Okay, so I'm assuming that the entire layer is now just going to be given by the overlap layer law or the logarithmic law. Or in other words, what will I write? The velocity profile will be now given by u star is equal to 1 over k ln y u star by nu, right? So y u star by nu plus b. So this is the logarithmic law that we wrote down. So now I'm going to talk about a pipe whose radius is r, and let's say we are going to use a cylindrical coordinate system in which r is the radial coordinate. So y I will replace with r minus small r, because y is the distance from the plate. So in this coordinate system, r minus r will be the distance from the plate. So this is the approximation that we are doing. Yeah. Now, r minus, no, we had defined y to be the distance from the plate. So now the distance from the plate would be just capital R minus small r. U star, U star. Look at your notes and see whether this is consistent. Whatever we wrote in the last class should be consistent with this expression. So you feel a little more comfortable with that expression. Where U star was defined as, what is the name of U, what is it called? Friction velocity, which was defined as square root of, okay, so U star is the friction velocity. Okay, so if this is the case, let's actually calculate the average velocity in the pipe. Okay, so right now we have just taken it as an approximation. Average velocity. How do we calculate average velocity? Let's call it, let's say V is equal to 1 by, so it's a circular pipe, pi r square integral 0 to r u into 2 pi r dr. Is that right? So this is the velocity integrated over the entire surface divided by the surface area. Yeah. So we know the expression for u. So substitute and integrate and see what the velocity, average velocity is. You can just go ahead and integrate. It will take a couple of steps. So So that's what you need to integrate now, right? There are two different terms, one containing log and then there was a constant multiplied by r. You get something like that. That's what I. So, and the typical value of k is 0.41 and b is 5. And if you substitute, you get v by u star is equal to 2.44 ln ru star by nu plus 1.34. Okay, so that's the average velocity that you get for a turbulent flow in a pipe if you assume that it's given by the overlap layer completely. Now we are directly going to now evaluate the friction factor. So there are two ways of doing it. One is what we followed in our laminar flow calculation, where you calculate the pressure drop, connect it with the turbulent, the wall shear, okay, and then do it. Or you can do it in a simpler fashion here. If you look at this quantity V by U star is V divided by U star was defined as square root of tau W by rho. So that means V by U star square is rho V square divided by tau W. Correct? And what is the connection between tau W and the definition of friction factor? You can just check your notes and tell. In terms of wall shear stress. It will be there where we introduced a friction factor for the first time. Yeah, somebody says 8 tau W by rho V square. Check whether it's there now in the notes. Yeah. So that means tau W by rho V square is what? Or rather rho V square divided by tau W is equal to 8 by F. Right? So if I can actually directly therefore write down a relation V by U star is equal to square root of 8 by f. Agreed? And why am I writing down? Because I already know the expression for average velocity, but the average velocity, the relation between average velocity and friction factor, we now know. So therefore, I can immediately say that the expression that we really have, this expression, okay, is nothing but root of 8 by f is equal to 2.44 ln, not y, r u star by nu plus 1.34. Okay. We really want to get it in terms of Reynolds number, so we want to make that logarithm in terms of Reynolds number. Can you make that logarithm, argument of that logarithm in terms of a Reynolds number? The argument r u star by nu, so u star if I replace with square root of tau w by rho, okay, and again write it as tau w rho v square, where v is the average velocity, I can write that square root term in terms of f again. So basically I get Reynolds number times square root of f by 8, that argument. Check whether it's right. Yeah. In other words, what we are saying is simply square root of 8 by f is equal to 2.44 logarithm of Reynolds number based on the radius times square root of f by 8 plus 1.34. If you rewrite 1 by square root of f is equal to 1.99 log Reynolds number based on the diameter times root f plus, minus 1.02. That's the relation that we wanted, the relation between Reynolds number and the friction factor. So let's just go through what we have done and then maybe so we started looking at the flow through the turbulent flow through the pipe, okay, and we said the velocity profile is simply given by the overlap layer law, which is the logarithmic law. We assume that that is the case, and then we went ahead and calculate an expression for the average velocity, and the expression for the average velocity came out to be that the average velocity, average expression for the average velocity came out to be that. Okay, our intention is to calculate friction factor. So we wanted to calculate friction factor, which we could have done by calculating the pressure drop and calculating the wall shear and so on. Instead of that, what we have done is we knew that average velocity, wall shear stress, friction factor are all related. So we are essentially exploiting that relation, which is nothing but that, and rewriting the velocity profile in terms of friction factor and Reynolds number directly. That's all we have done. And therefore, we ended up with this expression, okay, which is 1 by root f is equal to approximately 2 ln Re root f minus 1.02. As opposed to what was in laminar flow, that. Okay, I'm putting the suffix d to just show that the Reynolds number is calculated based on the diameter and not on radius. Okay, so here you can actually see given Reynolds number, if you want to calculate friction factor in laminar flow, it was much easier. But how is it in turbulent flow? Yeah, there. So I have changed it. So here we had RV by nu, okay, which you can write it as Reynolds number based on the diameter divided by 2. This is RED. So there will be a log of root 2 that will come, which I think is adjusted in that prefactor. Can check. Yeah, so what I wanted to tell was, given Reynolds number, how would you calculate F? Using this expression is straightforward. Okay, it's a nonlinear expression which contains a square root and a logarithm. Okay, so what can you do? How do you solve nonlinear algebraic equations? Yeah, go ahead. You want to tell something? Graphically, is that the only method that you have learned in your third semester? Tell. Numerically, yeah, what methods have you learned? Okay, I don't know. Probably the best is Newton-Raphson. Okay, check. So there's a nice expression where you can apply all those methods and calculate. Okay, it's a very complicated equation, but it's an extremely useful equation. And therefore, typically those problems are illustrated using this equation. So that's where you'll see the use. Anyway, okay, so this equation, so remember we assumed overlap the logarithmic law and calculated it, but instead of that, let's say you wanted to calculate, it is compared with experiments and the actual coefficients, okay, have been replaced a little bit. 1 by root f is equal to 2.0 ln RED root f minus 0.8. Yeah. So this seems to be fitting very well with the experimental data, which means that our original approximation of replacing the velocity profile just with the logarithmic law was a good approximation, because we have ended up with equation very similar to what is found experimentally. Okay, so that's the only justification for replacing or using the logarithmic law. So you should be really using this expression if you want to calculate friction factor, which is a straightforward relation. Okay, so if Reynolds number is not very large, okay, which is let's say 10 raised to 4, 10 raised to 5, then you could use this direct relation, which is a empirical fit. But this is going to be useful because I want you to calculate what is delta P proportional to let's see which one shall we, let's do velocity first. Velocity to the power of question mark. What is that question mark? for laminar flow and turbulent flow? Can you find out? So what I'm saying is that there is another equation which is valid over a small region. Okay, so that's a useful approximation. So use this useful approximation and tell me delta P is proportional to what power of V for laminar flow and turbulent flow. So for laminar flow, of course, you should know, you should use your older expressions that we already knew, and turbulent flow, you can use this nicer expression 0.316 times RE to the power of this. Question like, for example, you double the flow rate of, you double the velocity, what happens to pressure drop? You want to calculate, what would you do? That's what I'm asking. So the first thing is to write delta P in terms of friction factor. That's our basic definition. Okay, substitute for F and see what is the power of V that you get. So for laminar flow, F is that, turbulent flow, F is, okay, so it's almost square dependent. Okay, so if you double the average velocity in laminar flow, the pressure drop will increase, it will double, but for turbulent flow, it will go by 4 times almost. If the flow rate is fixed, what is delta P proportional to D to the power of question mark, where D is D for the laminar and for the turbulent flow. Okay, flow rate is fixed through the pipe. What is going to be the dependence of pressure on diameter or radius? Are you following what I'm saying? Just trying to exploit, look at those relations and see what the area's dependencies are. Okay, so you will see this that it goes as d to the power of -4 for laminar flow and close to -5 for turbulent flow. Okay, so that means that pressure drop decreases as you increase the the size of the Q is the volumetric flow rate. Yeah. So see, you want to pump something fixed, okay, and now you have the choice of selecting the pump as well as the size of the pipe. Okay, what is that you would want to do? Would you take a smaller pipe or would you take a bigger pipe? If you take a smaller pipe, then it says that the pressure drop is going to be larger and larger. Okay, so then what you would want to do is you want to reduce your electricity consumption. You would want to go for a less pressure drop. Then you would say that, okay, you will take a larger pipe. But what is the issue with taking larger pipe? The initial cost becomes extremely high, maintenance will become large. Okay, so therefore there is a competition now. When you are asked to design something, whether you want to reduce your electricity usage or whether you want to reduce other costs. Okay, so that's the relevance of this relation. And of course, laminar and turbulent, whether that flow rate also makes a difference. Okay, just I have written down a relation at the end, U max. Okay, that's the maximum velocity divided by the average velocity. What is maximum velocity by average velocity for a laminar flow? Okay, so we did that, or you did it in one of these quizzes. So show that it's actually this factor for your turbulent flow. Okay, just use the expression that you already have and try to manipulate. Okay, and you should try to get this relation. Try it. We'll talk more about this tomorrow.